Well, welcome back to Dynamics. We are in the Foundations series of Dynamics, and this is video 5 in Foundations. We are doing some sample problems. This is the first one in kinetics, and we're going to do Newton's second law. I've created a problem here, and imagine that we've got a box being dragged along the ground. And there's some force pulling up at an angle of 30 degrees. The box has some mass, and we're going to have it accelerate at some rate of change of speed. And let's have some friction between the box and the ground. Let's use a coefficient of friction of 0.1. Let's give a few more known pieces of information. Let's have the box have a mass of 100 kilograms. Let's do everything in metric. So the acceleration due to gravity is 9.81 meters per second per second. And I can either give us a force and find the acceleration, or give us an acceleration and find the force. Let's give an acceleration of 0.1 meters per second squared. Now, in kinetics, we're going to use Newton's second law, which basically says that force is equal to mass times acceleration. And because all of these things are vectors, we end up using force equals mass times acceleration twice. Once for everything in the x direction. Let's label x and say to the right is positive. And once for everything in the y direction. Let's label the y direction and say that everything up is positive. We want to know what force is in this rope. Think if you could put a scale in there, kind of like a scale that you might use to hold up a fish. Let's draw ourselves a little fish here. And you say, I wonder how much our fish weighs. And so you put a scale in the rope, and oh, our fish weighs 10 pounds. That tells us the force of the fish. It tells us the weight of the fish. It tells us the force in the rope. So imagine that we put one of those scales in this rope. What would it read? That's the force. That's the thing we're looking for. Again, this should all be review from physics. So we're given the diagram. We're given that the mass is 100 kilograms, that the coefficient of kinetic friction is 0.1. The acceleration is 0.1 meters per second squared, and we are being asked to find the force in the rope. So, solution. How do you solve a Newton's second law problem? There are different ways. Different physics books will do it differently. I'm going to go ahead and show you the way that we'll use in the rest of this course in dynamics. And that is through drawing two diagrams. The first diagram is called the free body diagram. Free body diagram. We will refer to it as the FBD. Now, in a free body diagram, we can compress the box down to a point and show all of the forces. So what goes on a free body diagram is forces. And here we have the weight of the box, mg, pushing down, the force of the rope pulling up at an angle of 30 degrees, the ground pushing back up on the box. We call that the normal force. You might also see it as force normal. We'll use both of those probably somewhat interchangeably. We do use lots and lots of different symbols in engineering, and we have to get used to that moving around. And then there's a frictional force that will oppose motion, the force of friction, and it is the coefficient of friction times the normal force. There's the FBD. Now we draw the mass times acceleration diagram. As always, I do encourage you to press pause at any time and maybe even go back a little bit and listen to things again, or to catch up. Pause is your friend when watching videos. So now we're going to draw the other diagram. It's called the mass times acceleration diagram. We will call it the MAD. And it has the masses and accelerations, the mass times acceleration. Well, this box is only going to accelerate in the x direction. It's not moving vertically. So we only put an MAX on this diagram. We only, on the MAD, put the actual direction of motion. All right. So step 3 is where we take all of the forces from the FBD and set them equal to the mass times acceleration on the MAD. So F, the sum of the forces in the X, again to the right is positive, equals MAX. So we have to look at all of these forces on the FBD and say, how much of this force is in the X? Well, none. How much of this force is in the X? Well, I'm going to say that F times the cosine of 30 is the part of that force that is in the X. How much of the normal force is in the X? None. How much of the friction force is in the X? All of it, but to the left. So we will say minus the coefficient of friction times the normal force. And now we have taken care of every single force in the X. We move over to the MAD and say how much of MAX is in the X direction, and well, all of it, and positive. So there we have the, wait a second, get my colors right. There we have the sum of the forces in the X. Now we sum the forces in the Y. Sum of the forces in the Y is equal to MAY. So we look at each color, each force, and say, how much of mg is in the Y? Well, all of it, except it's down, and we're saying that up is positive. So minus mg. How much of F is in the Y? Well, part of it, and it's upward. It's this part right here of F is in the Y direction, and that is F sine 30. How much of the normal force is in the Y? Well, all of it, and it's up, so positive. And how much of the friction force is in the Y? None of it, so it doesn't go in this equation. Now we come over here to the MAD. How much of the MAD is in the Y? None of it. All right, there we go. Now we have two equations, equation 1 and equation 2. Let's use the check mark method to see how many unknowns we have. From the check mark method, we put a check over things we know and we circle things we don't. So let's go through this first equation. Do we know f? No. Do we know the cosine of 30? Yes. Do we know the coefficient of friction? 0.1. Do we know the normal force? No. Do we know the mass? 100 kilograms. Do we know AX? 0.1. So in this equation, we have one equation and two unknowns, F and the normal force. Let's go to the second equation. Do we know M? Yes. Do we know G? Yes. Do we know F? No. Do we know the sine of 30? Yes. Do we know the normal force? No. And we know 0. So now we have two equations, two unknowns. This has just gone from being a dynamics problem or a physics problem to a math problem. We have two equations, two unknowns. I would use my trusty TI 200 calculator. I've got it right here in front of me. And in that, I would type in the word solve, and then I would start filling in the equation, but putting in the numbers. So F is a letter, I don't know it, times the cosine of 30, I do know it, minus 0.1 for the coefficient of friction, times, I'm just going to use N in my calculator, equals, mass is 100, and acceleration is 0.1. Then I type and, I type in the next, minus 100 times 9.81 plus F times the sine of 30 plus N equals 0. And then in my calculator, I put a squiggly bracket and tell the calculator, what do I want? I want F and I want N. And when I type this into my calculator, it tells me that F is 118 newtons, and N, which I'm not being asked to find, but it is 921, I'm going to call it 922 newtons. So here's my answer. And the problem is over. We wanted to find the force that it would take to accelerate a 100 kilogram box being pulled at an angle of 30 degrees to an acceleration of 0.1 meters per second squared with a coefficient of friction of 0.1. And we use Newton's second law. The key ingredients are the free body diagram and the MAD, and then the equation for Newton's second law in both the x and the y. X